given a polynomial function, let's look at how to find all of the real zeros of the polynomial. So this is different than before when we were given either all or some of the zeros as a starting point. Here we don't have any of the zeros given, so we don't have a value to just begin with a synthetic or long division. So we're going to walk through a couple theorems that can help us to get started. So first we're going to use a rule that's called Cauchy's bound for real zeros. So what this does is it helps us to find an interval where we can focus. So rather than having to look everywhere for possible x-intercepts or horizontal intercepts, this is going to help us to narrow down our focus to just a certain interval. So to use the formula for this bound that's given in our section 3.5 notes, we need two numbers from our function. We need the largest coefficient and we need the leading coefficient. So thinking in absolute value, so the numbers that we have to work with here in our coefficients are 3, 1, 6, and 2. So the largest coefficient is 6, and we're going to call this m in our formula. The leading coefficient is the coefficient in front of the term that has the largest exponent. So we call that a sub n, and in this case it's the 3 that's in front of the x cubed. So the formula for Cauchy's bound is an interval with brackets, and we're going to take the opposite of m over a sub n minus 1, and then m over a sub n plus 1. So plugging in the two values that we just found, so for us this is going to be the opposite of 6 over 3 minus 1, and then 6 over 3 plus 1. So 6 divided by 3 is 2, so negative 2 take away 1, we have negative 3, and 2 plus 1 we have positive 3. So what this is telling us is that all of our horizontal intercepts will be in this interval. Guaranteed. So when we graph this function on our calculator in a later step, we're going to adjust the window settings to use this negative 3 as our x minimum and this positive 3 as our x maximum, knowing that we won't be missing any intercepts outside of this. The next step is that we're going to make a list of possible rational zeros. So we're going to use a rule that's called the Rational Roots Theorem. So to use this theorem, we're going to be looking at two numbers from our function. We need our constant term, and we're going to be looking at factors of the constant term. So the constant term is the one that doesn't have any variables. So for us, that's the 2. So we're going to make a list of values, we call them P, that are factors or things that divide into 2. So things that divide into 2 are 1 and 2, positive and negative. Then we're also going to look at our leading coefficient. So we used this in the last step, so this is still that positive 3. So we're going to look at factors of positive 3 are 1 and 3. So the rational roots theorem then says you can make a list of potential rational roots by taking the p and dividing by the q. So we're going to take the positive and negative 1 and the positive and negative 2. And we're going to divide that by positive negative 1 and positive and negative 3 and list out all the possibilities. So 1 divided by 1 is 1. 2 divided by 1 is 2. 1 divided by 3 is 1/3. 2 divided by 3 is 2/3. So this is a list if you count the plus and the minus. So we have 4 positive and 4 negative. So this is 8 potential zeros. So any rational numbers that show up as a 0 or a horizontal intercept on our function must be in this list of 8 potential values. So our next step is we're going to graph this function on our calculator using the values that we found in our interval on step 1. So let's take a look at that. So on my calculator, I went ahead and in my y1, I put in my original function that we were given. And then notice here for my window settings, I changed those to -3 and +3 instead of the default settings. Everything else I left just the same. So when I hit my graph button, this is what I saw on my calculator screen. So think about those values that we had in our list. Here's -1 and here's +1. Neither one of those appear to have a horizontal intercept. Here's -2 and here's +2. Neither of those have a horizontal intercept. So then we had -1/3 and +1/3. So that would be about right here would be -1/3. About right here would be +1/3. So this looks like that might be a potential 0. So I'm going to jot that down. So a potential 0 is at +1/3. -2/3 and +2/3 also don't seem to have any zeros. But I just need one as a possible starting point. So what I'm going to do is I'm going to do a synthetic division using the 1/3 that I found from my graph. So that's coming from this value on my graph. And then I'm going to take the coefficients from my function for synthetic division. So 3, -1, -6, and 2. I bring down the 3, and then multiply, add, multiply, add. So 1/3 times 3 is 1. When we add -1 plus 1 is 0. Multiplying, we get 0. Adding, we get -6. Multiplying, we get -2. Adding, we get 0. So that remainder of 0 tells me that +1/3 really is a 0 of this function. And if we know a 0, we know the factor that goes with that is going to be x minus 1/3. Think about the values that you found in your quotient here. The -6 is going to be your constant term. 0 is the x term, and then 3 is the coefficient for our x squared term. So here's what we've figured out so far. We've taken our original function and we have factored it to be x minus 1/3 using the 0 that we found on our graph that we put into our synthetic division. And then now we have 3x squared minus 6. So we want to use this quotient that came from our synthetic division to find the remaining zeros. So think about working with your 3x squared minus 6. When would that be equal to 0? So adding 6, we have 3x squared is equal to 6. Dividing by 3, we have x squared is equal to 2. So x is either plus or minus the square root of 2, taking the square root of both sides. So between what we found from our graph and in our synthetic division and what we found by setting our quotient equal to 0, we have found that this function has 3 real zeros. Those real zeros are x equals +1/3, x equals positive square root of 2, and x equals negative square root of 2. All three of those values are also found on our graph. If we look back at the graph at the top here, the +1/3 is the one that we were using for our synthetic division. But if you look at these two other x-intercepts, horizontal intercepts that we found, this one is relating to that positive square root of 2. This one is the negative square root of 2. So this cubic function, a degree 3 function, we found are 3 real zeros.